Okay, now I'd like to talk about the beginning of Chapter 2, visiting vertices, Hamiltonian circuits, and then leading into the traveling salesman problem, which is by far the most significant and important topic that we'll have talked about so far. Very important problem in computer science as well as mathematics. Maybe some of you had a toy like this when you were kids. I looked for it on the internet and couldn't find a picture of it, but it looks like this. It's called a dodecahedron, and then in the real toy, which is made out of plastic, there are little shapes cut out of each of the faces here. Then there are other plastic pieces that are correspondingly shaped, and the child is supposed to learn that you have to put round shapes in round holes and square shapes in square holes and so on. A gentleman by the name of Hamilton in the 1800s, 1860 or so, posed the following puzzle. Take this dodecahedron, and it's a three-dimensional shape, but it does have vertices, and it does have edges. And so we can think about it as being a three-dimensional graph, and Hamilton's puzzle was visit each vertex exactly once, and then return to the vertex from which you started. If it seems kind of familiar, remember Euler circuits were travel along each edge exactly once and return to the vertex where you started. Now we don't have to travel along each edge, but we do have to visit each vertex. Because the graph is three-dimensional, it's hard to visualize. So let's do some simplification. Let's take this three-dimensional solid shape, and because the faces, like the red and the violet and blue, faces are not significant, let's go ahead and just dissolve them. And so you see this kind of wire mesh, three-dimensional wire mesh shape, where the edges and the vertices are there, and the faces are gone because they're not important. But it's still three-dimensional. And so here it is again. What we're going to do now is cut it and lay it open. So let me point out some similarities between the three-dimensional picture and then the two-dimensional picture that you get once the graph has been laid open. Here's a pentagon, a five-sided figure. Here's that same pentagon in the two-dimensional picture. Here on top, for example, is another pentagon. Here it is. Here on the left is another pentagon. Here it is. And so on. Some of these are on the back, and they're getting laid out around the outside. And then the very back pentagon, which you can't see except in the shaded lines here, is actually laid out to the outside. So the entire outside is this pentagon stretched out. You know, when you make a two-dimensional map of the globe, things get distorted as they're stretched out, and that's the case here. So now the question is still the same. Here's the graph in two-dimensional form. Start at any vertex, find a circuit that visits each vertex exactly once and returns to where you started. The question is, can that be done for this graph, or is it impossible? And if it is possible, what's the strategy for finding such a circuit? A Hamiltonian circuit, it's called. Well, let's see. Let's just try trial and error. Suppose I go along this edge. Now I visited this vertex, and then 2, and then 3. And now you see if I come over here to 4, there may be a problem. I think I had better go in here. 4. Let's go along 5, 6, 7, 8, 9, 10, 11, and let's see. Now I think I'll go 12, 13, 14, 15? Then how about 16? And now you see I've sort of done the inside. I'm at this vertex, and so I'll come back out to the middle ring, 17. And I've already been down here, so I need to go up here, 18. Now I'm done with the middle ring. Let's go back outside, 19. And then let's go 20, and we'll return back here to say vertex A where I started. Now look at this. This is a circuit. I started at A and I go around a while and then come back to A. It's not an Euler circuit. Here is an edge, for example, that I didn't use, but it is a Hamiltonian circuit. It visits every vertex exactly once. So yes, Hamilton's puzzle does have a solution. Okay, other than a mathematical curiosity, why might you want to do something like this? Well, let's take somebody's giving you this beastly summer job. Let's change the task just a little bit. Instead of inspecting curbs or painting curbs, suppose you're inspecting stop signs. And so there's a stop sign at perhaps each intersection, or at least some of the intersections. And you need to go around to each intersection, or maybe more realistically, you're inspecting the controlling box at a stoplight. And so you have to go around and visit each vertex. Doesn't matter what order, but you only want to go to each vertex exactly once and then return to your starting point. That would be an example of a situation where you'd want to find an Hamiltonian circuit, and we'll consider other more realistic ones in a moment. Question, here's a graph. Does it have a Hamiltonian circuit? And if not, what's the smallest number of edges that you have to add so that it does? So let's look at this example and the one following and just get some idea maybe of a strategy or see how easy or hard this type of problem is. So suppose I start here at vertex A and I decide to go along edge J. Then I have two choices. I could go down to vertex C or down to vertex D. Suppose I go here. Now I know I'm going to have to go over here and visit vertices E and F, so maybe I go over here. Now you see there's trouble, because as I complete this loop, I'm going to have to come back to vertex D. There's no way to get back over here to vertex A without going through D again. And if you think about it, even if I had chosen another path from vertex B or even another path from vertex A, there's no way to visit every vertex without going through vertex D a couple of times. So does this graph have a Hamiltonian circuit? No, not as it stands. What about adding edges? This is not an Euler circuit problem or a Chinese postman problem, so this time we'll say we're free to just add an edge. It doesn't have to be a duplicate of an existing edge. And that's pretty easy to settle. If I, for example, add edge BE, then this graph certainly has a Hamiltonian circuit. I could go from A to B to E to F to D to C and back to A. So in this case, with simply adding one edge, this graph could be made to have a Hamiltonian circuit, but the graph as given did not. What about this one? Hamiltonian circuit? If not, how many edges might you have to add? Well, let's see. Let's start here at vertex A again. By the way, it doesn't matter where you start, right? Because you're going around to visit every vertex anyway, and so once you have a circuit that starts at vertex A, you could just trace it around but begin at vertex B and trace the same circuit. If I start at vertex A and go to B, and then if you notice there's kind of a outer ring and then part of an inner ring, and remember Hamilton's puzzle, so maybe we want to go and kind of pick up things from the outer ring and the inner ring and either do those alternately or perhaps do all of the outer and then the inner. In this case, maybe alternate is a good way to go. So after vertex B, how about we go to E, then back out to C, and then we're on a roll. Let's keep going here, here, and then how about we do the dipsy-do in and get vertex I, come back out to the outside to vertex N, and then dip in to get vertex M, back out to get vertex L, and then I think I can just keep following my nose around here and come back to vertex A. And that's certainly not an Euler circuit, but that wasn't the question. It is a Hamiltonian circuit. So answer to this is yes. Remember when we were finding Euler circuits, we came up with a easy check. You would check if the graph was connected and if every vertex had even valence. Do you think that might be the same situation here? Well, here for example, vertex M has valence 1, 2, 3, 4, 5. So this graph has a Hamiltonian circuit, but it has at least one vertex of odd valence. So that's not the right check. Might there be another one? In particular, is there a computer algorithm for this? Can you program a computer so that it can look at a graph and efficiently tell whether the graph has a Hamiltonian circuit or not? It's beyond the scope of the course to show what the answer to this question is, but let's just state it. No. Even though Hamiltonian circuits look a lot like Euler circuits, in some sense they're harder. For Euler circuits, a computer can be programmed to find one easily if the graph has one at all. For Hamiltonian circuits, nobody knows how to do this. We'll talk about brute force ways where you just keep trying and trying and trying until something works, but that's not efficient. Nobody has an efficient algorithm for solving problems like this on a computer. And that's actually a problem of interest, because what might you want to use this for? Well, let's go back to the airline routing example. And perhaps an airline wants to route passengers between cities, or in particular in the traveling salesman problem, the job of the salesman is to visit each city exactly once and return back to where he or she started. And so now the edges are not just regular edges, but we're going to put weights on these, most often corresponding to physical distance. So it's a certain number of miles between Minneapolis and Cleveland, a certain number of miles between Detroit and Cleveland, and so on. And then as I think about traveling around and visiting every city and returning, I'd like to do that in the shortest distance possible. That's an interesting problem for somebody who's planning logistics for a company. And the fact that there's no efficient way of solving it has a lot of implications for what kinds of things are reasonable to be able to do or not. Let's look at a concrete example, a small example. Here are just 4 cities, Cleveland, St. Louis, Minneapolis, and Chicago, and the approximate distances in miles between each of these cities. So it's a weighted graph. Vertices, edges, and then the edges have numerical weights on them. As I indicated, the traveling salesman problem says, from a given starting point, say the city Chicago, find a route that goes around and visits all of the cities and then returns to the starting point. That much would be find a Hamiltonian circuit. But the traveling salesman problem adds the following stipulation: find the shortest such route. So I can go around among the 4 cities and return to Chicago in a number of different ways. We want the shortest such way. Okay, let's look in detail now at the traveling salesman problem. In particular, some possible ways of solving it. The traveling salesman problem says find the shortest Hamiltonian circuit. And so here's one possible way of solving the problem that was just posed. Find all possible Hamiltonian circuits. Just list them all, brute force. And then find the distance of each of those Hamiltonian circuits and pick the shortest one. Very straightforward approach, at least conceptually simple. Let's check out how much work this might be. First, let's take a detour into a branch of mathematics called combinatorics, which is just a fancy way of saying when you're counting possibilities, how many do you end up with? Suppose you're ordering pizza and you're going to choose one of the 3 types of crust the company offers, and then choose one of the 5 types of meat toppings the company offers. And the question is, how many different types of those pizzas can be ordered? Well, there are 3 types of crust, and then each of the crusts can be paired with 5 types of meat. So like with the first type of crust, there are 5 different pizzas that can be ordered with that type of crust. And then I go to the second type of crust and they're the same 5 choices of meat. So here's another 5 possibilities. And likewise with the third type of crust, there's still the same 5 meat choices. So here are another 5 types of different pizzas that can be ordered. And so 3 5s, the answer to this type of question is to multiply the number of choices in each of the sets of choices that you have, assuming at least that the choices are independent. So here, the choice of meat has nothing to do with the type of crust. And so there are 15 different pizzas that can be ordered. Okay, well, how about this problem with the traveling salesperson and the Chicago, Cleveland, St. Louis, Minneapolis city, and we're trying to find the shortest Hamiltonian circuit. Well, let's count how many possibilities there are. If we're going to do this problem brute force by just finding all of the Hamiltonian circuits and then choosing the shortest one, how many would we have to look at? At Chicago, there are 3 other cities. We're going to choose one of them and go there. And then once we've gone to another city, say Cleveland, I don't want to go back to Chicago until I finish going around to the other cities, so now there are 2 cities left to choose from. And once I go to one of those, then my hand is forced. There's one remaining city that I haven't visited. I have to go there and then return back to where I started from. So at the first city I have 3 choices. At the second city I go to I have 2 choices. At the third city I only have 1 choice, which is really no choice at all. It's just one possibility. And likewise, then I return back home. So how many possible circuits? Well, 3 choices times 2 choices times 1 choice is 6 possible choices. 6 possible Hamiltonian circuits. There is one thing to realize. We don't have to look at all of them actually, because if I have a Hamiltonian circuit in mind and I go around it, say, counterclockwise, if I were to take the same circuit but go around the opposite direction, clockwise, of course I'd have the same distance because I'm using exactly the same edges, just in the opposite order. So in fact, I only have to look at half of these. So how many different circuits must I examine? 6 divided by 2 equals 3. By the way, there's a notation that goes with this. Maybe some of you have seen it before. You have this 3 times 2 times 1 business. Another way of writing that is called 3 factorial, and you use the exclamation symbol. That just means take the integer that's given, multiply it by itself, and then subtract 1 and multiply, subtract 1 and multiply till you go down to 1. We just commented that there are 3 possible Hamiltonian circuits that we need to look at for this problem. Here actually are those 3. So Chicago, Cleveland, St. Louis, Minneapolis, and back, and then another possibility would be Chicago, Cleveland, Minneapolis, St. Louis, and back, and so on. And we've added up here the distances as you go along. So 349 plus 541 plus 5 is 62 plus 425 equals 1877. 3 possibilities have length 1877, 1985, and 2040. The Hamiltonian circuit says find the shortest one. It's right here. So this is the shortest Hamiltonian circuit. And that means it's the solution to the traveling salesperson or traveling salesman problem. Not too bad, right? Not too many possibilities to look at. What if the problem gets bigger? Suppose instead of 4 cities, we have n cities, where n could be a large number, like n equals 100, or n equals 1,000, or n equals 60, or something like that. How about possibilities now? When I'm at the first city, how many choices are there? Well, there are n minus 1 other cities. I'm at one of them, and there are n total, so there are n minus 1 other cities that I could go to. Once I move to another one, now there are n minus 2 remaining cities, and I can choose any of those. Once I'm to the next city, then there are n minus 3 remaining cities that I could go, and I can choose any of those, and so on. So the number of choices, just as before, goes down by 1 each time. Finally, I get to the last city. I have just the one choice, and then I return to my starting city. So how many does this work out to be? Well, there are n minus 1 choices at the first selection, and then n minus 2 choices, and then n minus 3 choices, and then n minus 4, n minus 5. I can't list them all because I don't know how big n is. So in math, what we'll do is dot, dot, dot. Here's a pattern started where you're multiplying numbers. Keep multiplying numbers, and then how's this going to finish? Well, you'll get down to 3, and then 2, and then 1. And remember, we only have to look at half of them because of the clockwise, counterclockwise thing. So let's write this in simpler form. This is n minus 1 times n minus 2 times n minus 3, and so on. We saw the factorial before. This is n minus 1 quantity factorial divided by 2. That's the number of Hamiltonian circuits that are possible when you have n cities. And you should know this. This is something to memorize. Let's look at some numbers then. Here's the formula. So number of cities, and then let's compute n minus 1 factorial divided by 2 for several cases and see how big it is. For our original problem, there were 4 cities, and 4 minus 1 is 3 factorial. 3 factorial is 6, divided by 2 is 3. How about when there are 8 cities? So 8 minus 1 factorial divided by 2. That's 7 factorial divided by 2. And now there are a couple of ways to go. 7 factorial is not too big, and so you could literally just take 7 times 6 times 5 times 4 times 3 times 2 times 1 on your calculator, divide by 2. Or perhaps you know where the factorial key is on your calculator. Look for the exclamation mark. In particular, if you have a graphing calculator like the TI-83 or something like TI-84, something like that, look in the math menu and then maybe PRB for probability, and you'll probably be able to find a factorial key there. Either way, when you work it out, this turns out to be 2,520. You might want to do this yourself and make sure you get that answer. Well, 8 is not that much bigger than 4, but 2520 is certainly a lot bigger than 3. I can do this problem by hand, but I really don't have much urge to do this problem by hand and look at over 2,500 possibilities. And if we went to 12 cities, now it's getting just totally ridiculous. Almost 20 million possibilities to look at. 16 cities, 653 billion possibilities. This is, by the time we get to 2520, it's completely out of the question of doing it by hand. By the time we get much bigger than this, 19, 20 million, it starts to come out of the question to do by computer. This probably is out of the question to do by computer, or at least you'd need a very fast computer and let it work for a while. And 16 cities is not that big. I mean, a real problem may have 20, 30, 40, 60, 100 cities, and if you think about how big this factorial gizmo is going to be, it's just completely undoable. Even if the fastest supercomputer in the world can't do these kinds of problems. Hamiltonian circuits are hard. And yet, these are the kinds of problems that computer scientists and applied mathematicians and other people want to solve. So what do? Well, in real life, we might have situations that are similar where we want to do something, and to find the exact answer or to find the best possible way to do something is pretty difficult. But most of the time, it doesn't matter that we get the exact answer, best answer. Maybe just a good one is good enough. We do that in real life all the time. I want to get somewhere. I'd like to get there the fastest possible, but I'm not going to sit down with Google Maps and plot out every possible way that I could go. I just hope that I check out a few and hope for a good one, and hope that it's close to optimal even if it's not optimal. So in computer science, you call this using a heuristic approach. The brute force approach is just too much work, so give it up. Don't do that. Settle for an algorithm, we'll call it a heuristic algorithm, that with a reasonable amount of work will find a good solution. Not necessarily the best. We'd like for it to be the best, but it's probably not going to be. But since it's too much work, it's impossible to find the best solution, at least to guarantee that you found the best solution. An algorithm that works reasonably fast and finds a good solution may be good enough. Let's look at a couple of heuristic algorithms for the traveling salesman problem. They're called nearest neighbor and sorted edges. We'll take them in that order. Nearest neighbor is very intuitive. It says pick a city, start at it, and then go to the closest city that you haven't yet been to, and then do that process again. Once you're there, go to the closest city you still haven't been to, and go to the closest city you still haven't been to. Keep going until you get back where you started. Let's use this problem we had before as an example. Suppose we choose to start at Chicago. And then I have 3 choices of other cities to go to, but the 300 is less than 349 and 425, and so I'm going to pick the 300 and go to St. Louis. Now I'm at St. Louis. I have 2 choices. I can go to Cleveland, I can go to Minneapolis. It's closer to go to Cleveland. Let's do it. Then I'm at Cleveland. Now I only have 1 choice. I have to visit city Minneapolis, and then I have to return to Chicago. So the distance that I ended up using is 300 plus 541 plus 774 plus 425. And that works out to be 2040. Is that the best you can do? Oh, I don't think so. Remember that we did this problem brute force because it's a small one. We could do it brute force, and we came up with a a circuit that had length 1877. This one is another one that we found. It has length 2040. In fact, it's the longest of the three that we found. And this is the price you'll pay for using a heuristic algorithm. It's easy to use, but it may not find the best solution, and in this case it certainly didn't find the best solution. Well, how bad did we do? From a science class, you may have done percent error calculations, where you take, in science we'd say maybe the expected value minus the observed value divided by the expected value times 100. Here, let's take the heuristic length, the length found by the heuristic algorithm, and the optimal length, the length found by a brute force approach, if you could possibly push that through. All right, if I crank the numbers, my heuristic algorithm found a circuit of length 2040. We know that the optimal length from brute force is 1877. Then let's convert it to a percentage by multiplying by 100%. And if you work this out, you get about 8.6%. What's that saying? In this example, the nearest neighbor route, the route that the nearest neighbor algorithm found, is about 8.6 or about 9% longer than the best possible route. So, is that a problem? Well, maybe not. In real life, if you had a task to do and you were paying, say, 10% more than you needed to, that might not be too bad. If this route was 800% longer than the best possible route, then that's a real problem. But 8%, 9%, maybe that's not too much of a problem. And so sometimes a heuristic algorithm can miss the best solution but still be close enough that we'll be happy with the result. That's the nearest neighbor algorithm. Let's look at another algorithm, completely different. The sorted edges algorithm. This is gonna, the name of the algorithm is sorted edges, and so that's exactly what needs to happen. First thing you're going to do is take the list of edges and sort them in increasing order. Then you'll start applying the algorithm. You'll go through your list and add the shortest edge that you haven't yet used, as long as it doesn't add more than 2 edges to a vertex. So as we're adding edges, we can never get to a situation like this where we put in 3 edges to 1 vertex. The reason is we're trying to build a circuit, and so if there are more than 2 edges coming into a vertex, we're not going to be able to visit that vertex exactly once like you have to with a Hamiltonian circuit. Another thing you can't do is complete a circuit that misses any vertices. In other words, that prematurely completes a circuit. So if I'm throwing in the edges, I can't do something like this. This is a circuit, but it's not a Hamiltonian circuit. It doesn't visit all of the vertices, vertex M in this case. So you go through, you look at your edges. If it passes the test that it doesn't do this and it doesn't do this, then you put that edge into the circuit. Let's look at an example. Here's the graph. It has weights on the edges. And the question is, as before, find the lowest cost Hamiltonian circuit, or at least a low cost Hamiltonian circuit. All right, I've done part of the work already. Over here on the side, I've taken all of the edge lengths, say DE is length 0.5 and AD is length 0.6 and so on. I've listed all of those and then I've sorted them into increasing order like this. Now, let's go about building the circuit. Remember, I can't put more than 2 edges to a vertex and I can't prematurely complete a circuit that doesn't include all the vertices. So, first candidate for the circuit is edge DE. I look at it, can I put it in? Sure. Adding this edge doesn't violate either of those 2 conditions. How about edge AD? That would be here. And that's fine. that wouldn't put more than 2 edges into any vertex or prematurely complete a circuit. How about edge AE? That would be here. That would be a circuit with just 3 vertices, so we're not going to use that one. How about AB? That's up here. Yes, that would be fine. So we'll put that one into the circuit. How about CD? No, there are already 2 edges coming into vertex D. Can't put that one in. BE? That would be here. Looks good at first, but if you think about it, that would make a circuit going A, B, E, D, and back to A. That's not a Hamiltonian circuit. It wouldn't visit vertex C, so no, we can't use that edge. AC? No. Already have 2 edges coming into vertex A. CE? That's here. Yes, I think so. Notice something about this algorithm. It works differently than nearest neighbor. It doesn't keep adding the edges end to end to end and building the circuit that way. Instead, it throws in edges kind of at random around various places around the graph, and then supposedly they hook together at the end. How about, well, are we done? I don't think so. We don't have a circuit yet. I mean, here we're just stopping at vertex C. BD? No. Vertex D already has 2 edges coming into it. How about BC? That would be here, and yes, I think so. We can put that one in. And we're finished. What's the Hamiltonian circuit? Well, let's list it by listing the vertices in the order that we visit. For example, we could start at A and go to B and go to C and then E and then D and back to A. That's A to B to C to E to D and back to A. All right, there is a circuit, a Hamiltonian circuit. It may or may not be the shortest one. I'm not going to even go into that. There are a lot of possibilities here. We have 5 vertices, so there would be a lot of choices to consider. May not be the shortest one, but probably shorter than what we would do if we just randomly picked something. That's sorted edges. Let's look at a couple more examples, one of each. Same graph, let's do this one 2 different ways. Here's a graph, a weighted graph, and I want to apply the nearest neighbor algorithm from vertex A. When you say you're going to use the nearest neighbor algorithm, you have to say which vertex you're starting from, or you have to pick a vertex to start from. And if you start from a different vertex, C, there's no guarantee that you're going to get the same circuit as if you start at vertex A. So here, for whatever reason, somebody told us we're supposed to start from vertex A. Remember back how nearest neighbor works. You start at A and you go the nearest place you haven't been yet. So out of 103, 93, 78, and 99, 78 is the shortest. We're going to go along to vertex D. Then what's nearest? 135, 121, 112. 112 is the smallest. We'll go to vertex B. What's next? I only have 2 choices now. I can't go back to A yet. So 84 or 88. 84 is the smallest. Now I'm at C, and now I'm really out of choices. I have to end up at vertex A, and I haven't been to E yet, so I had better go here and then along here. So what's the circuit? In the order that I visited, I went from A to D to B to C to E and back to A. And I could add up the edges that I used and find out how long this is if that were asked. All right, let's do the problem using sorted edges. In sorted edges, you don't have to specify a starting vertex. Doesn't matter. What you do have to do, though, is go through the work of sorting. So if you go through and carefully pick out the edges one at a time in increasing order of length, the smallest number I see is a 78. That's edge AD. Then there's an 84. That's edge BC. Then there's an 88. That's BE. There's a 93, that's AE. There's a 96, that's CE. There's a 99, that's AB. There's a 103, that's AC. And by the way, CA, AC are the same edge. I don't care which way you would list that. Let's see, then to finish, there's a 112 somewhere, BD, and a 121 CD, and finally a 135, that's DE. So that's most of the work right there, to go through and sort all of the edges in an order of increasing length. Okay, let's start the algorithm. Remember, you can't put more than 2 edges into a single vertex, and you can't prematurely complete a circuit. AD, can I put that in? Yeah, I think so. So let's take the 78 and put it in. How about BC of length 84? Sure. How about BE, the 88? So no more than 2 edges into any vertex yet, and does not complete a circuit. So we can put this one in. So far so good. AE, 93. That's here. And that doesn't complete a circuit, if you look carefully, and doesn't put more than 2 edges into any given vertex. So yeah, we can use AE. And then CE, nope, more than 2 edges into vertex E. AB, nope, more than 2 edges into vertex A. AC, no. BD, see, where's BD? BD, nope. CD, yes. And so we'll put that in. And actually, we're done then. We've found a circuit. It goes from, say, A to E to B to C to D and back to A. Notice that this is a different circuit than the nearest neighbor from vertex A found just in the previous slide. So here is the circuit that sorted edges found. Again, it may or may not be the best one. Probably isn't. Might be a good one. Notice something that happened here. We thought we were on such a roll. Initially, we're using all of the shortest edges, and that's great. And then somehow, right near the end, we got forced into using this 121, which is one of the longer edges. So this is an unfortunate thing that happens with these algorithms. Sometimes you're on a roll, and then at the very end, you're just forced into using something that obviously is not a very good choice. But that's the way the algorithm works out in this case. All right, again, Traveling salesman problem, very important problem in computer science, very useful problem in terms of routing and traveling and those kinds of tasks that airlines or delivery routes and so on would require using. You're going to do your first project is going to be along the lines of this topic, and so that information will get out to you shortly. And then in conclusion, remember Euler circuits and things that went with Euler circuits are pretty easy problems for computers. And now we found that Hamiltonian circuits and the traveling salesman problem that goes along with it is a pretty hard problem for a computer. Very hard problem for a computer. So that's what we have to say about this topic. Thanks.